is equal to 65 millimeters. Okay, so now let's look at shear stress distribution below the centroid. So now, based on the rule, this will be the analysis direction. Okay, remember rule number 3, the distribution starts from the furthest distance away from the centroid. Okay, so now our distribution, our thickness now will correspond to 2 multiplied by 0.02. So this is equal to 0.04 meters. So our limits is 0, y, and is 0.065 meters. Okay. Right. So from here, what we do now is we again find the first moment of area, Q of y, Q of z, okay, as a function of y. So this is twice. Okay. The width will be 0.02. The depth will be equal to 0.065 minus y, and 0.065 plus by y multiplied by half. Okay. So what is happening now is I'm going to draw the constant shear stress line. This is our constant shear stress line, and this is where our y is. Okay, so we are taking this area, right? Because the analysis starts from the furthest distance away from the centroid, and we're looking at below the centroid now. So from here, this will be equal to 0.065. So it's equal to 84.5 times 10 to the power of minus 6, and then minus 0.02 y squared. Now, does this number look familiar to you all? Okay, and you have seen this number 84.5 times 10 to the power minus 6 minus 0.02. If you go, when we look at over here, right, the numbers are exactly the same. Can you see that? Right? And I've shown you this before. Okay, so when I show you this before is when last week when we did the example, right? Remember, we wanted to find, right, the shear stress at the centroid from the top section or the bottom section. The maximum or the maximum first moment of area are the what? Are the same. So likewise, when you do the shear stress equation, right? Whether you take from the top or from the bottom with constant thickness, I highlight again, with constant thickness, the equation should be the same. Okay. So if you look at the constant thickness, right? So constant thickness, I'm going to color here. So this is the region of constant thickness. Okay, with constant thickness, right, the equation, whether you do from the top or from the bottom, is going to be the same. Okay, so from here, shear xy as a function of y again, so this is equal to 90 times 10 to the power 3 multiplied by 84.5 times 10 to the power minus 6 minus 0.02 y squared, and then the whole thing divide by 5.8133 10 to the power minus 6. Now this will be between 2 to 0.02 or 2 multiplied by 0. So this value will be exactly the same. It will be equal to 33.705 times 10 to the power minus 6 minus by what? Minus by 7.741 times 10 to the power 9. 7 point y squared. Okay. So from here we are going to sketch. Okay, we are now going to sketch the shear stress distribution. Okay, given all those numbers now. Okay, so now we are going to sketch. Okay, so I'm going to make the assumption that this line over here is my centroid. Let me shift this down a bit. Okay, that's about 0.03. Then I'm going to draw our axis over here. And then I'm going to draw our y-axis. So this is our y. This is our normal stress. Shear. Oh, no, yeah, right, Eugene. Come on, shearing stress. And this is our pen 20, 30, 40, and this is in megapascal, and then over here is in our meters, okay, or millimeters. Okay. Then we're going to draw our lines. Wrong color. Then we have another line. Then we have another line. Okay. So we know that from here, we're going to start from 0, right? And then we know if we go to point, if we want to calculate what value we have of the web. Okay, so if we look at this equation over here, right? If we look at this equation over here, this is 0.016. Oh, no, 0.16, correct. Okay. If we look at here, we substitute y equal to 0.015. Okay, so 9.483 power 6 minus 7.741 power 9 times by 0.015 times by 0.015, it will be 7741. Okay, 77, I'll do it again, 7741.483 power 6 minus 7.7 times by 0.015. Yep, 7.741. Okay, so this value over here, okay, so this value over here is 7.741. And the y distance is 35 millimeters. No, this is not 35. This is 15 millimeters. Right. So this is 0 and 35. Then it stretches itself, right? Then we go to look at this equation over here, right? We look at this equation over here. We plug in the value 0.015, so 32.705 power 6 minus by 7.741 power of 9 times by 0.015 times by 0.015. You get 30.963. Okay, so this over here. So the next point over here. So it goes straight up, vertically straight up. Why vertically straight up? Okay, is because of the thickness changes. Okay, 30.963 times 10, no need times 10 power 6, and this thickness is at 15, or position 15y. And then we have our maximum 32.705, because now we know that y is equal to 0. Okay, so 84. Yep, 82 point. So you have a value here, and this is equal to 32.705, and at 0. Okay, so we're going to have a curve looking like this, and then it will come back down like this. Okay, and we know that the function for this curve is equal to 32.705 times 10 to the power 6. Should not be minus, I do apologize, plus 6 minus 7.741 times 10 to the power 9 y squared. And this curve over here, right, this curve over here is a different curve with a different equation, which we have, which is equal to 9.483 times 10 to the power 6 minus by 7.741 times 10 to the power 9 y squared. Okay, so that's how you sketch the equation, or you sketch the distribution of the shear force, or sorry, of the shear stress. Okay, so anything else that I want you to take note? Yeah, no, nothing else that I want you to take. Oh, one thing I want you to see is two things I want you to observe: that the higher order coefficient did not change. Okay, so when you check for your exam or test, when this come up, okay, whether you're right or wrong, the higher order or the second order polynomial function coefficient is the same for both. Okay, and for this case, I elaborate again. For this case that you see, the maximum shear stress is at the centroid. So I want you to take note. Okay, for this case, not always. Okay, I repeat, not always. So for this case, right, the tau max occurs at the the tau max occur at the centroid. Okay, now it's not necessarily always the case. Okay, sometimes it is not. Okay, sometimes it's not. Okay, so before I go and show you sometimes it is not, anyone want to clarify anything in this question? Anyone, please?
Yeah, I have a question.
Yes.
Like, maybe you mentioned before, but I didn't mention. So, like, how do you identify the curve? Like, it's like smiling curve or sad face curve.
For this case, the higher coefficient is negative.
Oh, okay.
Okay, that's the only good question. That's the only reason.
All right, got it.
I have a question.
Yes.
Will we be asked to draw this diagram during the test?
I can ask you anything I teach, Lee.
Okay.
Okay. So that's the answer.
Yeah, fair.
Anyone? Tony?
At 15, why is it constant again?
Say it again.
At 15, why is it straight line again? Vertical line?
It's not constant. It's a stepwise function. It's a step, right?